right, so for today's lecture, we'll work through the entirety of the practice final exam. I'll explain everything along the way. If you have any questions as to why I did something a certain way, or why, why something is regarding the practice final, tonight is your time to ask, okay? This class session is primarily for you guys to learn and kind of go over the answers. I am recording this, and I'll post up the notes that I write, which will serve essentially as a as your solution key here. Okay. All right. So let's get started with the first set of questions. So you can expect something similar to this on the actual final exam, where I describe a scenario and I ask you to see which, if any, of the conditions have been violated. Okay? All right, so looking at this first problem, it says, we're looking at a study to understand the relationship between bright lights and headaches. And it says, we've got 80 randomly selected subjects, expose them to bright lights, 20 of them complain about headaches, 90 are exposed to less bright lights, and 12 complain about headaches. Are any conditions violated here? So here we're dealing with we've got two samples, and we're dealing with proportions. Okay, proportions because this is a categorical variable. We're looking at how many people experienced headaches or how many did not. Okay, or the percentage that did. And then when we look at the conditions, we have the independent and random condition. And this condition is met because both of our samples say they were randomly selected. If we look at the big population condition, this condition is also met, okay? If we think about what the population is, it's not specified in the problem, but the population would be everyone basically everyone in the world, or everyone who might be exposed to lights, which would pretty much be everyone in the world, right? Almost everyone in the world, okay? So this is a...
We're talking about humans,
right? Right. Okay, and then we have the large sample condition. And so for this one, because we're dealing with proportions, we need at least 10 successes and at least 10 failures. In each sample. So if we look at sample 1, we have 20 who have headaches, okay? Whether we call that a success or failure is arbitrary. And because we have 80 total, this means 80 minus 20 means 60 have no headaches. Okay, so both are greater than 10. Okay? As far as sample 2 goes, we have 12 with headaches and 90 minus 12, or 78, have no headaches.
You can't do it where like
you can't divide 20, 80, and 12,
yeah.
90.
I did it that way.
You can, and you should still get 20 and 60,
But that's
right?
okay to do that.
That's totally fine, right? You're basically just throwing a small extra step in there, which you're saying, p hat is 20 over 80, which is 0.25, and then you do 0.25 times 80, and then 0.75 times 80, and then you're going to get 20, and you're going to get 60 here. Okay, it's the same thing mathematically. Okay. Okay, and then so all of these numbers are greater than 10. So this condition is met. Or greater than or equal to 10. And so we would say no conditions violated. Okay, moving on. We'll take a look here. Okay, it says a researcher wants to make a confidence interval for how common a certain disease is. He finds 300 randomly selected subjects, finds 2% of them have the disease. Are any conditions violated? Yes, question.
Do you want to put the conditions?
Yeah, I was just going to write them here. Okay, so we have the independent and random condition. And this one is met because it says it was randomly selected. Okay. Randomly selected sample. And then we have the big population condition.
That's the same order, right?
I think so. I don't know. Maybe I've done it out of order. It doesn't really matter. Okay. I don't know what order I have them printed on the final. Okay. Just make sure the labels are
Okay, I'm
correct.
just considering that A, B, C will be the answer.
Okay. I guess I could check. Yeah, this would be A and this would be B. And then lastly we have C. Okay, big population condition. Okay, so the population here would be pretty much everyone in the world because we're looking for the prevalence of a disease, right? Okay, and then so this condition is met. And then finally we have the large sample condition. Okay, and then so here we're going to check n times p and n times 1 minus p must both be bigger than 10. Bigger than or equal to 10. Okay, and so we have n is 300 times 0.02. This only gives me 6. 300 times 0.98, which is 1 minus p, gives me 294. Okay, this one's bigger than 10, but this is not greater than 10. Okay. So the large sample condition is not met. Okay. Number 3, it says a student has to conduct a survey for a school project. He goes around the school campus and interviews people he meets. He finds data from 100 people and finds that 45 of them answered yes to his questions. Are any conditions violated? So here, right off the bat, we see the independent and random condition is violated because walking around the school will not produce a random sample. Okay. Yes, question.
For the final exam next week, would you include another answer choice where it's like
Multiple conditions violated
Yeah.
or something?
or would you just leave it the same like this?
It will probably be the same as this. Whatever it is, I will make sure none of the questions are ambiguous. So here, there is some ambiguity regarding the big population condition. May or may not be met based on the school size.
But because when we're given the school size, we can't prove or disprove them, right?
Right. So there is a you know, if, and this is true, if the independent condition is violated or the random condition is violated, then the other two conditions don't really matter, okay? If that one's violated, then the other one, it doesn't matter if your population is big or small, or if your sample is big or small. It's,
But then would you pick the one that more than one condition is violated, or would you just vote any kind of random if this was the situation?
yeah, I don't know. I'll make sure there's no ambiguity on the final, okay?
So it won't be like this.
It won't be like this, okay? So as far as this question goes, I know there's some ambiguity regarding the big population condition. There will be no ambiguity on the final, okay?
Ignore me. Move on.
He's just
All right. A company wants to survey its employees. It has 800 employees. It decides to select 100 of the employees randomly and interviews each of them. Are any of them conditions violated? So in this case, you know, it says random sample, okay? It says, you know, they were selected randomly, so the random condition is met.
Yes. It literally is the same.
And then, but the big population condition is violated. Okay, because the population is 800 employees. This is not 10 times bigger than the sample of 100. Okay, so in this one, it's clear that the big population condition is violated. Okay, so you can expect you know, a handful of questions like this, probably about 4 of them on the final exam. Okay, and then you'll have a bunch of questions where I give you a scenario, and you'll have related questions to these, okay? And again, the most important step in all of these is to recognize whether you have means or proportions, whether you've got 1 sample or 2 samples, whether you're dealing with hypothesis tests or confidence intervals, okay? So as we're looking through this problem, we see, okay, immediately we see the word confidence interval, so we're dealing with a confidence interval. And when we read through the problem, it talks about 2 different diets, cows getting 2 different diets. So we got, you know, 10 cows get diet 1, 12 cows get diet 2. Okay, so this also tells us immediately that we're dealing with 2 samples. Okay, and then as we read further in the problem, we see things like words like average, 15.2 pounds. So now we know we're dealing with averages or means, and it's a numeric variable. So here we've got confidence intervals, we're dealing with means, and we've got 2 samples, okay? And so I'm going to just go to the reference table, okay, where it says confidence intervals, means, 2 samples, and I'll copy this chunk and put it into our kind of our notes here. Now, you guys will want to make a note sheet, okay? Your note sheet needs to be you know, letter sized, and you can write on the front and back. So just 1 piece of paper writing on the front and back. If you want to use the formula sheet that I've provided for one of the sides, you can do that. If you want to rewrite them even smaller so you can fit other stuff somewhere else, that's up to you, okay? And then I've also created like a guide for inference, which is a little bit more verbose, kind of walking you through and saying, like, if this is the question, then this is what you want to do. You know, whatever you feel comfortable with, you can go ahead and use that, okay? So in this case, we're dealing with confidence intervals, means, 2 samples, and so we see the interval is x bar 1 minus x bar 2 plus or minus t star times the standard error. These are the variables that we need, x bar 1, x bar 2, s1, and s2, and we calculate the standard error this way, okay? So a lot of times I like to list off the values that I have. So I've got diet 1 and diet 2 for basically sample 1 and sample 2. And so my N for diet 1 is 10 cows. My N for diet 2 is 12 cows. My X bar 1 for diet 1 is 15.2. My X bar 2 for diet 2 is 12.6. My S1 is 4.1 pounds. And my S2 is 3.4 pounds. Okay? So a lot of times I like to go through the problem and label these just so that later on when I'm plugging them into formulas I don't accidentally use the wrong number. Okay? Sometimes you know, when we feel extra comfortable with these problems, sometimes we go straight to plugging in things and then we plug in the wrong thing and we get ourselves into trouble. Okay? So don't make dumb mistakes, all right? Okay. For a 95% confidence interval, what will be the center of the interval? Okay, the center is always the part before the plus or minus, so that's going to be x bar 1 minus x bar 2. So we're going to have 15.2 minus 12.6. The center of our interval is 2.6. For a 95% confidence interval, what will we use for t star? Okay, so we got 95% confidence. And our degrees of freedom is n minus 1, okay? We have two n's, but we're going to use the smaller of them, so we're going to have 9 degrees of freedom, okay? We go to our reference tables, we go to the t table, we go to 9 degrees of freedom, 95% confidence, our t star is 2.262. What is the value of the standard error? Okay, and so as far as the standard error goes, we're just going to plug in the numbers that we have. So we got S1 squared, 4.1 squared, over N1, which is 10, plus 3.4 squared, S2 squared, over N2, which is 12. Okay, we'll punch this into our calculator. 4.1 squared over 10, and then 3.4 squared over 12. 1.626. Okay, and then we'll create our 95% confidence interval. So I'm going to have 2.6, which is x bar 1 minus x bar 2, plus or minus t star, 2.262, times the standard error, 1.626. Yeah, so part 5, which was find x bar 1 minus x bar 2, that's 2.6. Okay. All right, so let's do that. 2.6 plus 2.262 times 1.626. I get 6.278 on the high end. And on the low end, I just do that and I replace the plus with a minus, and I get negative 1.078. Okay. So for number 9, it's saying, do we have evidence that there's a difference in the average weight gain? Here, let me just...
Since 0 is there, there's no evidence.
Correct. Okay, so we look, so we see that 0 is inside the interval. Okay, so this means it is possible, or plausible, it is plausible for the difference to be 0. It is plausible that the difference between mu1 and mu2 is 0, so we do not have evidence do not have evidence that there's a difference in weight gain.
So we cannot write there is no difference. We just
Yeah, you cannot say that there is no difference. All you can say is that we don't have evidence of a difference. Okay. If, here we only did the study with 10 cows on diet 1 and 12 cows on diet 2, okay? If we did a study with 100 cows on diet 1 and 100 cows on diet 2, maybe we would have evidence of a difference. Maybe, maybe not. We don't know, okay? So we can't say that there is no difference. All we can say is right now that there's no evidence of a difference, okay? Okay, if we made a 90% confidence interval instead of a 95% confidence interval, what would happen? Okay. Yeah, T star would change to a smaller value. Okay, we can see that in the T table. In the T table, instead of 2.262, we would use 1.833. Everything else would remain the same, but making T star smaller would make our interval more narrow. Okay. All right. That is 5 through 10.
wait. You forgot to answer.
Did I go? What? How would it compare? This would be narrower. Okay.
So because 0 is not in the range there is a difference. That's basically the answer, no?
Well,
So our answer, okay, so if I replace, so I wasn't asking this, but even though we make it more narrow, 0 is still in the interval. So even at 90% confidence, we don't have evidence of a difference, okay? Now if we dropped it down to 80% confidence, okay, and this is not, you don't have to worry about this anymore, okay? But if we dropped it down to 80% confidence, then 0 would not be in the interval, and we would say we have evidence of a difference. How does this work? Basically, when we say I have evidence of a difference at 80% confident, I'm less confident in my answer there, okay? It's like, how confident do you have to be before you, take a stand and make an opinion, right? Some people are going to take a stand even though they're not even though the percentage confidence isn't super high, they're going to just say, let's go for it, okay? Other people will say, like, I want to wait until the percentage is higher before I'm going to make a claim or take a stand on this thing, okay? And that's all the differences. Okay, but at a lower confidence level, your interval gets more narrow. That's what happens. Okay, so with the next one here, we're going to the ruler and yardstick factory. Who makes rulers and yardsticks these days? Mead? I don't know. Okay, so we're going to look at this problem. And it says a machine is suspected to be defective. The yardstick it produces are supposed to be 3 feet long. We're measuring a sample of 40 yardsticks and find that the average length is 3.02 with a standard deviation of 3 feet. Is this evidence that the machine is producing yardsticks that are too long? Okay. And when we're looking at this, we see things like p-value and a hypothesis test. So we know we're dealing with a hypothesis test. Okay. We're looking at a numeric variable, the length of a yardstick, and we see things measured as the average length, so that's an indication, and we also see a standard deviation. So both of those things indicate that we're dealing with means. And as we look through this problem, we only see one sample of 40 yardsticks, okay? So here we're dealing with a hypothesis test, one sample, and dealing with means. So I'm going to copy this section right here, hypothesis test, means one sample. We'll use this, and okay. And then I think I think it's a good idea to kind of list off the stats that we need. So we'll need our n, which is 40 yardsticks, our x bar 3.02, and our standard deviation of 0.03. Okay. And if a yardstick factory has a standard deviation of 0.03, it's not a very good yardstick factory, but that's beside the point here. Before I majored in statistics, I majored in industrial engineering, and I had to focus on quality control. So, and that's how I got into statistics, because it was on statistical quality control. So, anyway, you learn about stuff like that. It's a good stuff. Okay. All right. So our null hypothesis. Oh, I'm sorry. That would be number 12. Okay, well, actually, let's do number 12 first. What would our hypotheses be? Okay, mu would be equal to mu 0. Okay, what is the mu 0 that we're going to be using? 3. Okay, we want our yardsticks to be exactly 3 feet long. Okay, and then the alternative is this evidence that the machine is producing yardsticks that are too long? Okay, so our would be greater than 3. Okay, so based on that, we can answer number 11, and we will say this is a one-sided test. Okay, and then number 13, what's the value of the test statistic? Okay, our test statistic is t. So first we're going to find our standard error, which is s over the square root of n. So we're going to plug in 0.03 divided by the square root of 40. And we're going to get a tiny number, 0.0047434, I believe. Okay, I'll go ahead and type that out for you. 0.03 divided by the square root of 40. Okay, and that's what we have there. And then,
wait, go back to the calculator.
Yeah.
So, yeah, I see 4.7, but you wrote it as something else.
It says times 10 to the negative 3. I guess I should change this to norm 2. Okay, and there you go.
Yeah, I never got this.
Yeah, it's scientific notation. That's should have been covered somewhere in your math journey here. Okay, and then so our test statistic t is x bar 3.02 minus mu 0, 3, divided by our standard error. Okay, and then we punch this in and we get 3.02 minus 3 divided by, I'll go ahead and just type in answer and equal, and I get 4.216. So far, so good? Okay, we're going to look up our p-value now, okay? So because the alternative has a greater than sign, our p-value is equal to the right tail area. Okay, we're going to have degrees of freedom equal to 40 minus 1, or 39 degrees of freedom. We go to our table. We don't see 39 degrees of freedom, so we round down and we will use 30 degrees of freedom. Hope you're okay.
Is there a version of the table that contains all of those?
Yes, but
No.
not on one page, okay? They have, back in the day, there used to be statistics reference manuals that were like this thick, and it would just be like pages and pages and pages of the T table or the F table or whatever, you know. There's all these other tables for all sorts of other tests that you can use, and they would just have sheets and sheets of these things. Today we have a computer, and we just use that, okay? So to be honest, you know, you're learning how to look up these things on the table, and I think there's merit in that, but to be honest, when I do statistics for whatever else thing, I just use the computer, and the computer spits out an exact p-value. And here, you know, we only say the p-values between certain numbers. The computer can tell you actual things. Okay, find the p-value for this test. Okay, so we're going to use 30 degrees of freedom, and we're going to look for the number 4.216. Okay, so at 30 degrees of freedom, we see 4.216 is larger than the last number there, 3.385. Okay. What did I say, 3.385? Yeah, okay. And so what this means is that the corresponding tail area, the corresponding right tail area, which is our p-value, is less than 0.001. So that means our p-value, whatever it is, we don't have an exact value, but it is less than 0.001. We go to that column heading, and we see it's 0.001, so our p-value is less than that. So number 15, we would reject the null hypothesis. Okay, we're assume alpha is 0.05. Our p-value is less than alpha, so we reject the null hypothesis. And number 16.
So when we say our p-value is 0.001, we pretty much need to say, when we say our tail area is 0.001, we pretty much saying our p-value is also.
Correct. So we're going to reject the null hypothesis, and we'd say, you know, we have evidence that the yardsticks are too long. And then number 16, if the conclusion you just made was wrong, what kind of mistake did you make? Okay, so if we rejected the null hypothesis and that was a mistake, by mistake, then that is a type 1 error. Good?
But having this p-value makes it very hard to make a mistake, right?
You know,
Even if it's less than zero.
it would be surprising. It would be quite surprising. Okay, I don't want to say impossible, but quite surprising if that happened. Okay, and over here it says researchers believe that 14% of the population is left-handed. A local school district wants to decides to see if their students have a different proportion of left-handed people. The school has a total of 1,500 students. They randomly select 90 of them for the study, and they find that 15 are left-handed. Is this evidence that the proportion of left-handed students is different from the population proportion? Okay, so here we see that we're dealing with proportions, and if we look through it, we only see one sample, right? It's just one sample of 90 students, okay? And as we scan through these questions, we see we're dealing with a confidence interval. Okay, so we got confidence interval, proportions, one sample. Okay, so I'm going to go ahead and pull this segment out. Confidence interval proportions, one sample. Okay, and let's kind of list off the data that we'll need. Okay, so we have X, which is how many people that were left-handed. We see that 15 are left-handed. We have an N, 90 of them. I guess that's it for the data that we have. Okay, so the sample proportion 17 would be P hat. P hat is 15 over 90. And that's going to be, 1/6 or 0.16667. Really 0.16 with a bar over the 6, okay? What is the critical value that we would use for a 90% confidence interval, okay? This is just one of the 4 values. Anytime you do confidence intervals for proportions, there's 4 values you need to know. Okay, and we see for 90%, that value we need to know is 1.645. So we'll plug that in. We'll say Z star 1.645. Okay. The next question asks, what is our standard error? The standard error is given by that formula, the square root of P hat times 1 minus P hat over N. So I'll plug in 1.667 times 1 minus 0.1667 divided by N, which is 90. And I've gone ahead and done this calculation, and what I get was 0.0393 as our standard error. I hope that matches what you found. All right, the center of the interval is P hat, okay? The center is P hat. The center is always the part that comes before the plus or minus, okay? So in this case, 1/6 or 0.1667, okay? And 21, make a 90% confidence interval. So we'll go ahead and do that. So we're gonna have, so I'll just do one. Let me just do the fraction 1/6 plus 1.645 times 0.0393. Okay, and so. On the upper side, we get 0.2313. And then on the lower side, I'm going to do 1/6 minus this, and I get 0.1020. Okay, and depending on where you rounded, maybe your last digit is slightly off, okay? So this is our confidence interval. All right. 22. Based on your interval, is this evidence that the school proportion at the school is different from the nation? Okay, so the national percentage or proportion is 14%. Okay, what we see is that, the confidence interval for our school contains the value 14%. Okay, so that means 14% is a plausible value for the proportion at the school.
So you would say no difference.
Yeah, so we would say we do not have evidence that there's that our school's proportion is different.
sample proportion is bigger than the average. Like right now, for example, our proportions suggest we have 16% that are left.
So, yeah, I mean that there's no. I mean that's a silly question, right? It's like saying is 16 or 17% bigger than 14%? The answer there is yes. Okay, is your sample proportion different from the population? Yes. The question is not is our sample proportion different, but is the population proportion different from this reference value of 14%? And that's when we perform statistical inference. If we just want to know, is this selected sample different? The answer is almost always going to be yes. But the question is, does that then imply that the respective population is that different? Okay. Okay, let's look at this set of questions. Here it's talking about, we're going to buy some Jolly Ranchers and Starburst candies. And the bag of Starburst contain 80 pieces, 12 of them are cherry flavored. The bag of Jolly Ranchers has 70 pieces and 14 of them are cherry flavored. And we want to know, does this provide evidence that Starburst and Jolly Ranchers have a different proportion of cherry flavored candies? Okay, so here we see things that we're dealing with a hypothesis test. We are dealing with proportions because we're talking about whether a candy is cherry flavored or not. That's a categorical variable. And here we have two samples. Okay, so we got hypothesis test, proportions, two samples. Let's use these values here, or these formulas. Okay. All right, and then let's go ahead and label all of the values that we'll be using. Okay, so sample 1 will be the Starburst, and there we have a total of 80 pieces. Our N1 is 80, and our X1, which is how many that are cherry flavored, is 12. This gives me a P hat 1 of 12 over 80. Which is 0.15. Okay, sample 2 will be the Jolly Ranchers. We have a total of 70 pieces of candy. N2 is 70. Our X2, we have 14, which makes our P hat 2 14 over 70, or 20%. Okay, so I think it's useful to kind of write out your numbers here. This will help keep everything straight later. So 23 says write the appropriate hypotheses. So our null hypothesis is easy. It's always P1 is equal to P2, okay? Or it could also equivalently be written as P1 minus P2 is equal to 0. The alternative, when we look at the problem, it says, do they have a different proportion? So we're going to need to use P1 is not equal to P2. Or we can write P1 minus P2 does not equal 0. As far as 24 goes, we're looking for our overall P hat, which is going to be X1 plus X2 quantity over N1 plus N2. So here I've got 12 plus 14 over 80 plus 70. I get 26 over 150. And that gives me a P hat of 0.1733. Okay. For a hypothesis test, what is the test statistic? Okay, so we're going to have to get our standard error, which is P hat times 1 minus P hat, so I'm going to have 0.1733 times 1 minus 0.1733 times 1 over 70 plus 1 over 80. Okay, 1 over n1 plus 1 over n2. Okay, this is going to be some number here. Okay, and I get 0.06194. Does that sound reasonable? Seems reasonable to me. Huh?
Yeah.
Okay. What did I say? Or 06195. Okay, so that's our standard error. So our z-score is the difference between p hat 1 and p hat 2 divided by our standard error. So I get 0.15 minus 0.2 over 0.06195. And I get, rounding off to 2 decimal places, I get z is equal to negative 0.81. So to get our p-value, okay, the alternative has a not equal sign, so the p-value is equal to 2 times the tail area. Okay, z is negative, so our tail area is the area to the left. Tail is equal to area to the left of z. So I go to my z table and I'm going to look up negative 0.81. At negative 0.81, the area to the left is 0.2090. So my p-value is 2 times my tail area. So I'm going to have p-value is 2 times 0.2090. I get a p-value of 0.4180. Okay, so our p-value is 0.4180. What is the conclusion we make? Okay, our p-value is greater than alpha. This means we do not reject the null hypothesis. And we would say we do not have evidence that there's a different proportion of cherry-flavored candies in Jolly Ranchers and Starburst. Good? Great. Okay, moving right along. Okay, so here we're going to look at caffeinated drinks, see if they improve reaction time. Okay, and so here we have when we look through this problem, we see that we've got 2 samples, and we are dealing with means, right? We're looking at the reaction time, which is measured in milliseconds, and you know it gives us a standard deviation. So we've got means. We have 2 samples, and then looking at the questions, we see things like p-value and test statistic. So we know we're dealing with a hypothesis test. Okay, so using the hypothesis test for means of two samples, we'll go ahead and use these things right here.
Question.
Yeah.
Anyway, you're gonna test us two different questions in some subject, meaning are we gonna repeat hypothesis tests using two samples in different section, different research, different question, you know what I'm talking about? Probably not, but I just wanna make sure if it's okay for me to cross.
Oh no, you might see hypothesis test means two samples twice on the final. Okay, I'm not, just because you did it once doesn't mean it will not appear again. Okay, so it is possible, and I'm not gonna tell you that expect this.
So
but
I don't want to dismiss all those.
yeah, you don't want to just start drawing X's on your papers here, saying like I did this. That's done. Okay. Same with the our conditions violated. Okay. Just because one problem said it was the independent random condition was violated doesn't mean that another problem can't have the same condition violated. Okay. Or sampling methods. Just because one was simple random sampling doesn't mean that another one can't be simple random sampling. All right. Okay. What should the hypotheses be? Oh wait, before we do that, let's list off the values that we have. So we have sample 1, which will be the caffeine, group with caffeine, and then sample 2 will be no caffeine. All right. All right, and then so we have N1, X bar 1, and S1. And we'll have N2, X bar 2, and S2. Okay, so 30 people in group 1. We got N1 is 30. X bar 1 said the average was 580 milliseconds, and the standard deviation is 110. As far as N2 goes, we've got 25 in that group. The average reaction time was 640, and the standard deviation was 130. Okay, let's see here. For 28, what would our hypotheses be? The hypothesis, the null hypothesis is easy. It's that mu1 is equal to mu2, okay? Or we can also write mu1 minus mu2 equals 0.
But isn't it asking for one side?
That's the null hypothesis, okay? The null hypothesis always has an equal. The alternative says, you know, we want to know, does caffeine improve reaction time? Okay, so when we're talking about improving reaction time, what does that mean? It means, did you get faster or did you get slower in responding? You got faster in responding. So should your reaction time be smaller or bigger? Your reaction time should be smaller. Okay, so we would expect the group with caffeine, mu1, to be less than the group with no caffeine. Okay? So you want to read the problem carefully, and just because it says improves doesn't mean it goes bigger or whatever. Okay? In this case, an improvement in reaction time means your time went down, right? Okay, 29. What is the observed difference in means? Okay, this is just, you're taking X bar 1, which is one mean, and X bar 2, and you're getting the difference between two means. So you get 580 minus 640, you're getting a difference of negative 60, and this was measured in milliseconds. So number 29 is negative 60. Number 30 is asking what is our test statistic. Okay, so the test statistic, requires us to find the standard error, which in this case is going to be 110 squared over 30 plus 130 squared over 25. When I punch this out, I get 32.85 or something around there. And so our test statistic t is going to be x bar 1, 580, minus x bar 2, 640, divided by my standard error, 32.85. And I get a test statistic of negative 1.826. Hope that's good with everybody. Okay, 31, we're going to look up the p-value. All right, so our alternative hypothesis has a less than sign, so that means our p-value is equal to our left tail area. Okay, our t is negative, and that works out because when we see a negative sign, we basically just look that up in the table, but it changes from right tail to left tail. Okay, we're going to use degrees of freedom what? N minus 1, so we're going to have 24 degrees of freedom because we have two n's, we're going to use the smaller n. So we go to 24 degrees of freedom, and we're going to look up 1.826. Okay, it's in between these two columns, which means our corresponding left tail is in between 0.025 and 0.050. Okay, so the left tail area, which is our p-value, is between 0.050 and 0.025. Okay, so that means our p-value is also. Okay, so I'm going to just write 0.025 is less than my p-value, which is less than 0.05. Did I make a mistake here?
Yeah.
24. So we would pretend there's negative signs in front of all these numbers, right? So 1.826 is in between these two numbers, okay? And then that means our corresponding left tail, because we're changing everything to negative, is going to be between 0.05 and 0.025. So, yeah, so 32, whatever our p-value is, we know it's less than 5%, okay? So our p-value is less than 5%, so that means we reject the null hypothesis, okay? And we say we have evidence that caffeine improves reaction time. Okay, and then, and if that was a mistake, that would be a type 1 error. Okay, because we chose to reject the null hypothesis. If it was a mistake to reject the null hypothesis, that's a type 1 error. Okay. All right, and then so here it says in a certain city, a study was conducted to see if the police department and fire department have a different proportion of minority employees. All right, and so we randomly selected 200 employees from the police department and 200 employees from the fire department. Okay, so when we're looking at this, we're dealing with two samples. We're dealing with proportions, and here it's talking about hypothesis test. We got hypothesis test, proportions, two samples. Okay. So let's do this. Okay. And so again, I think I like to just go through the problem and label all of my values. Okay, so sample 1 will be police, okay? And sample 2 will be the fire department. We've got a total of 200 people in the police department. We have 80 minority employees, which gives me p hat 1 to be 80 over 200 or 0.4. In the fire department, 200 people in our sample. X2, we have 50 were minority employees, which gives p hat 2, 50 over 200, 0.25. Okay, as far as the hypotheses go, the null hypothesis is P1 is equal to P2, or P1 minus P2 is equal to 0. And then the alternative
Not equal.
is that they're not equal, right? Because we're just asking, do they have different proportions? So P1 is not equal to P2, or P1 minus P2 not equal to 0. The overall p hat would be x1 plus x2 over n1 plus n2. So I've got 80 plus 50 over 200 plus 200. I get 130 over 400, and for that I get 0.325. So p hat is 0.325. 36, we ask what is the test statistic, so we'll find the standard error. We're going to plug in p hat 0.325 times 1 minus p hat, 1 minus 0.325 times 1 over n1 plus 1 over n2, which is 1 over 200 plus 1 over 200. And I take the square root of all of that, and I get 0.04684. Is what I have in my calculations. So my test statistic Z is p hat 1 minus p hat 2, 0.4 minus 0.25, divided by 0.04684. And I get a Z score of 3.2. (37) asks, what is the p-value? Okay, so again, the alternative has a not equal sign, so our p-value is 2 times the tail area. Okay, Z is positive, so our tail area is the area to the right. Tail is area to the right of Z. Okay, so at Z equal to 3.2, the area to the left, the area given in the table is at 3.20 is 0.9993, okay? Area to the left is 0.9993. Area to the right is 1 minus that, 0.0007, okay? So the p-value is 2 times that. P-value is equal to 2 times 0.0007, which is 0.0014. So at 38, we would reject the null hypothesis. We have evidence that there's a difference in the proportion of minority employees. Okay, I just made these numbers up for this problem, so I have no idea what things are like in real life. Okay, and then 39, what does it mean to commit a type 1 error? I've kind of run out of space on this page, so I'll just write the answer to 39 right here. So in a type 1 error, we are mistakenly rejecting the null. So and this means that in truth, you know, the police department and fire department have the same proportion of minority employees. But in reality, we conclude that they are different. Okay. Good. Great. So we just have this problem with the potatoes and then the problem with the dice, and then that's it as far as statistical inference goes. All right, it says potatoes are sold at the grocery store in 5-pound bags. You decide to weigh a random selection of 10 different bags, and you find that the average weight of those bags is 5.2 pounds with a standard deviation of 0.3. Is this evidence that the grocery store have a mean weight different from 5 pounds? Okay, so we look at this, we're seeing that we're dealing with a confidence interval. We're dealing with means because we're talking about the weight of potato bags, and we got one sample. This is confidence intervals means one sample. So we'll copy this part. Okay. T-table comes from the T-table. I'm sorry, the T-star comes from the T-table. That's fine. Okay. All right. How many degrees of freedom do we have? This is our first question. Well, let's list off our statistics. We've got N, we've got X bar, and we have S. So we're looking at 10 bags. X bar is going to be 5.2, and our standard deviation is 0.3. Okay. Degrees of freedom, N minus 1, 9 degrees of freedom. Center of the interval, what's that? That's going to be X bar, the part right before the plus or minus. So we're going to just plug in 5.2. Standard error, so 42. The standard error is S over the square root of N. So we have 0.3 over the square root of 10. And I'm getting 0.0949. Great. The resulting confidence interval, so plugging everything in, X bar, 5.2, plus or minus T star. So looking up T star, 9 degrees of freedom, 95% confidence. 9 degrees of freedom, 95% confidence, 2.262. Times our standard error of 0.0949. This gives me on the upper end I get, or on the lower end I have 4.985 to 5.415. This is what I'm calculating here. Is that good? Okay, 44, what conclusion do we make? So we want to see 5 pounds, right? So 5 pounds is inside the interval. So at 95% confidence, we do not have evidence that the mean weight is different from 5 pounds. Now, if we decrease that level of confidence, if we're willing to make a statement or make a claim at with a lower percentage of confidence, then we could say we have evidence of a difference, because probably 5 would no longer be in that interval, because it's just kind of on that on the edge there. All right, is this good? Yes, question.
Why is it that we do not have evidence? I know that with 0 involved,
Yeah, so in this case, we're not looking for the number 0, but because the question says, is this evidence that the bags at the grocery store have a mean weight different from 5 pounds? So here we want to know, is 5 pounds a plausible value for the mean weight? Is 5 pounds in the interval? And in this problem, it is. And so it is plausible that the mean weight is 5 pounds.
I was just like, I would assume that we do have evidence because it's in between the interval. But
Yeah, so, because it's asking, is it different from 5 pounds?
oh, okay.
Yeah, so we don't have evidence that it's different from 5 pounds.
So
But remember, our interval can never prove that it is equal to 5 pounds.
Okay.
So we can never use our interval to say that the mean weight is exactly 5. We can only say we don't have evidence that it's not 5, or that it's different from 5. Okay. All right, and then our last set of inference-related questions. And then after this, we just have kind of this other stuff. I don't know, non-calculation based questions.
Oh, that's on the quiz.
Okay, so it says a fair die should land showing the number 4 1/6 of the time. And you roll a die 100 times and count how many times it lands as the 4. Okay, so here we're doing a hypothesis test. We're dealing with proportions because we're talking about whether the die lands on the number 4 or not. And here we just have one sample. When we read through the problem, it says we rolled it 100 times. And then that's all it says for sample collection. So we're going to do hypothesis test, proportions, one sample. Okay, and then let's just list off the data that we have in this problem. So we have n, we've collected 100 rolls, and then our x, how many times did it land on the number 4? It landed on the number 4 20 times, which means our p hat is going to be 20 over 100, or 0.2. Okay, so the hypotheses is always p equal to p0, our null hypothesis. So in this case, we want to know is p is equal to, and in this case it should land 1/6 of the time. So you can just write p is equal to 1/6. That's fine. You can turn it into a decimal, but decimals and fractions are essentially the same thing. They're just numbers, right? Okay. And then the alternative is it different from 1/6? So here we would write, is p different from 1/6? The sample proportion, p hat, that's 0.2. Sorry. When performing a hypothesis test, what is the standard deviation of your sampling distribution? This is just a fancy way of saying the standard error. So our standard error is equal to the square root of p0 times 1 minus p0 over n. So in this case, we got the square root of 1/6 times 1 minus 1/6, 5/6, divided by 100. And when I do this calculation, I'm getting 0.03727. When performing a hypothesis test, what is your test statistic? In this case, we're going to do p hat minus p0 over our standard error. Our p hat is 0.2, our p0 is 1/6, and we're going to divide this by 0.03727. I get a z-score of 0.89. And so as far as making my conclusion, I would look up 0.89. I'm sorry, so my alternative has a not equal sign, so our p-value is 2 times the tail area. I would look up 0.89 in the z table, and I find that the area to the left of 0.89 is 0.8133, okay? So at z equal to 0.89, area to the left is equal to 0.8133, which means the area to the right, our tail area, is equal to 0.1 minus that, or 0.1867. So the p-value is 2 times that, or 0.3734. Okay, so we do not reject the null hypothesis.
Why are we taking the area to the right again?
Because we want 2 times the tail area. Our z-score is positive, so our tail area is the area to the right. Let me just rewrite this, it's kind of sloppy. Okay. This good? Everyone feels comfortable? We're all gonna ace our final? No? Of course.
Yes. Because of your help.
It's good. Okay. Let's all right. I'm gonna flip the slide and let's cover just these last handful of questions. Okay, so we've got these sampling methods. So Major League Baseball wishes to conduct a survey of its players. Instead of trying to create a list of all players from all of their teams, they randomly select 4 of their 30 baseball teams and they'll survey all of the players on those 4 selected teams. What kind of sampling is this?
Cluster.
That one is cluster, yes. Okay. Company wants to survey its employees. They take its master list of everyone, randomly selects 100 of them for the survey. What's that? Simple random sampling. And then lastly, we've got a toll bridge. Survey the drivers. Instead of trying to ask all the drivers, they're going to stop every 10th driver. So it's that systematic. Okay. Great. Okay, and then you've got a sample of, or a handful of non-calculation kind of definition and conceptual questions here. So let's see. A bar chart is used for what kind of data? What do we have here? This one's categorical, right? What do we use for numeric data? Histograms. Scatter plots for 2 numeric variables. But for 1 numeric variable, we got histograms, we got dot plots, we got box plots. Okay. Okay, in a normal model, approximately what proportion of data is within 2 standard deviations of the mean? 95%, right? That's from the empirical rule. Empirical rule also says what? Within 1 standard deviation, you got about 68%. Within 3 standard deviations, you have almost everyone, 99.7%. Okay, intercept in linear regression would be our predicted value when x has what value?
0.
When x is 0, right? You guys, what is the definition of the slope? That's probably a good one to know. Not the formula, but what's the conceptual? So the slope is how much we expect.
The variation, y based on the variation.
That's a coefficient of determination. Okay. Slope is how much we expect y to change when we increase x by 1, right? So if we add 1 to x, we expect y to go up or down by whatever the slope says, okay? If the probability of a and b happening together is 0, that means a and b are Mutually exclusive. What does it mean for A and B to be independent?
They don't affect each other,
That means they don't affect each other.
but they could happen together.
They could have, yeah, they almost certainly could happen together, yeah. Okay, for quantitative is another way of saying numeric variable. For a numeric variable, if there's only one peak in the histogram, how do we describe the shape? Unimodal, okay. What does it mean to be symmetric?
Symmetric.
It means you have just as many outliers above as you do outliers below, right? What about skewed right?
Yeah, more.
Skewed right would mean you have outliers to the right but not to the left. Skewed left would be you have outliers to the left on the lower side but not to the right. Okay, which measure of center is not heavily influenced by extreme outliers? The median, okay. What's another way to define the median, or conceptual definition for the median? The median would be the halfway point. What's the mean? The balancing point, okay. So, you know, kind of just go through some of your notes for chapters 1 through 6. You just need to know the conceptual definition-based stuff.
Is IQR a measure of center, or?
IQR is the measure of spread. Measure of spread. Measures of spread are IQR, standard deviation. The range, I guess, is factored in there. All right, you guys, it's been a pleasure. Good luck as you guys study. We'll see you guys next week.